industry people, but it's more biased or inclined towards academic research. So, well, I'll be focusing on EHR data, electronic health records related data. Why I have chosen this topic is like regularly most of our students or scholars or teachers, they have been focusing on that X-ray stuff or some kind of images and deep learning applications kind of fun stuff. But there is a lot of potential in the EHR data, as most of the countries are adopting EHRs, and many private hospitals have already started adopting. So there will be more data, volumes of data, and also there are a lot of data sets provided in Kaggle, GitHub, and a lot of other medical related websites. So it will be more easy for people to pick up. Well, I'm assuming you know the deep learning concepts, so I'll not be touching them most of the time. Yeah. And in addition to EHR, I'll, because that is what healthcare domain researchers think about. So I'll start with a simple deep learning application on X-ray data, COVID-related data. I'll show you a simple program, very simplified program which I had written some 2-3 years ago, just to tell you how to handle the data. And then one more application on EHR data, so that clinical related data, how do we, how do we learn patterns in them? So I'll show you some exploratory data analysis of EHR related stuff. And then I'll also try to discuss like how the data is represented so that we can apply neural networks to the data. So make neural networks learn the data, because all of you know, for the neural networks to process the data, they require a kind of a representation. So there are a lot of papers published in the literature, but I have selected a few of them, so just to give you a start. And for those of you who are already deep into healthcare domain related deep learning applications, well, I think, well, you can do multitasking while just looking at the slides. Yeah. So with this agenda, so we'll try to discuss a few simple deep learning models, like what regularly the students and the scholars and the teachers, design and implement in the we'll talk about different perspectives of the healthcare data. And then we'll talk about a few embeddings related to electronic health records. And then I'll discuss, if time permits, I'll discuss a few more models which are related to transfer learning and stuff. Means the already existing models are model weights are used, and then last few layers are customized. So that's another kind of a problem. So the last portion, if time permits, I'll cover. So what are the healthcare applications where deep learning can be applied? So we have diagnosis related data, okay, and the results and the treatment and the insurance companies, drug discovery and public health related, applications can be applied with the deep learning concepts. to get a better result. Who are all the people who are generating the data? So we have whose demographic related information, like age, okay, gender, which part of the city or which state or which part of the country they are presently in. Okay, anything related to patients is a kind of a data. Then the service providers, the companies, fee reimbursement, the doctor fee or hospital fee reimbursing companies, the pharmaceutical industries who manufacture the drugs, other governments, the regulators, other standard making bodies, and the research scientists. All of these people, all of these organizations and people, they generate lots of data. And you're pretty aware, once there is data, the researchers have got some kind of a, task at hand. So to apply our deep learning applications, we require loads of data, and these are the stakeholders who generate the data. So patients, as I told you, their demographic or gender or age, their lot of perspectives you can gather data about a patient, an individual. And who are the service providers? So the doctors generate data. They write a lot of prescriptions. They give out some diagnoses, like they take X-ray image or they take some other test related data, and then they diagnosis. They come out with a result. And then they also prepare reports. Then we have hospitals who maintain the electronic health records. Then the clinics, they have the test reports, like trial data and all. And then pharmacy, drugs, and every drug has got some identifier, and there is a lot of data again generated. So for instance, how do these providers of data, they interact with each other? So World Health Organization has published electronic health records, a manual for developing countries, a report, which I have shown you at the bottom. You can search it on the Google and then get it. So yeah, this is all the data. Okay, and so patient ID and registration details, lab, hemo or pathology, radiology, scan documents, previous medical records, disease classification and indexing, clinical data treatment, orders, results, so outpatient visits. So all of this, they're related to electronic health records. And who are the fee payers? So insurance companies, so people claim the bills, either hospital bill or a pharmacy bill, a drugs bill. Then fee payers can be individual fee payers or their employers may reimburse. So there is again, some kind of data exchange between the hospitals and some other government agencies or the employers related to how much he is entitled to and lot of stuff. And government schemes, like you visit the hospital and the government pays the bill. So there again, lot of data is generated. So this is all about fee payers data. And then pharmaceutical industries, they generate a lot of data, like the drug manufacturing companies. So they have a lot of clinical trials, come out with some formulae. They then test on certain people. And they also have to comply with the government standards, and they also share data with the researchers and the researchers innovate some drug formulae, and these companies start making drugs. So again, here a lot of data is generated. And there are regulators like Food and Drug Administration, Centers for Disease Control and Prevention, Centers for Medicare and Medical Aid Services. So these are all the US standards. Why I have put them here is like most of the data sets available in Kaggle or GitHub, they talk about these regulators. And of course, for India, we have this. I'm just sharing the link. So there is an article. Okay, and you can just look at it. There's a lot of information related to the standards, the nomenclature, and other stuff. So this is Lexology website. So that is about the Indian context. Okay, you can open the page and then start doing. Then regarding researchers' data, we have lot of trial data. The drugs when administered, so what are the impacts and what are the side effects, and lot of other studies are generated here. And of course, we have publications, innovations, patents generated by the data scientists. Now, what is all this health data about? So when you look at the data sets, you'll observe electronic health record data sets, or medical claims related data sets, or clinical notes of the doctors, or the medical literature, or continuous signals imaging data, something like you're regularly measuring the BP, or other where you are monitoring the signals, ECGs, and all those. So that is another kind of a data. Then we also have medical ontologies to show you the hierarchies. And then we have drug discovery data. So here we have from Ministry of Health and Family Welfare. So the standards are all mentioned here. Okay, and so you can just download the report and have a look at it. So we have some standards like this. Yeah, identification and demographics. So there is a standard for it, typical, and basic identity details of a patient. So I was telling you patient details are collected. So how is it? They're as per these standards. Then demographic standards, then Aadhaar or local identifier or government issued ID card number. So patient ID is required. Lot of them, you can see. And there is a coding system, logical observation identifiers names and codes, LOIN. This is used for tests, measurements, and observations. Similarly, you have something called SNOMED and a lot of it. Okay. What I mean to say is they're all getting regularized. So they're getting standardized. There are audits for these hospitals on these data as per ISO guidelines, and data privacy and security, information security. You know, all this is patient related sensitive data. Similarly, data integrity, data encryption, digital certificate. Okay. So pharma related, you have a lot of standards data. What is all this EHR data about? So adoption of EHR, whenever a hospital adopts electronic health records, it's all about collecting, storing, transferring, and analyzing patient data over a period of time in order to improve health outcomes. So this does not only mean IT adoption or computerizing records, but signals the fundamental behavioral changes among the stakeholders. Who are the stakeholders? We discussed at length in the beginning. Structural changes in the institutions, legal frameworks, policy makers, the government officers, how do they think? Okay, how policies are built, all of it will now start revolving chronic health records. What are the components? As I told you, demographics, medications, clinical reports, and continuous monitoring data, medical codes, medical images, all of these are all put together an electronic health record. And what is the workflow like? The inpatient and the outpatient data. Inpatients, right from the moment of admission, about the complaints he has got. And then they have continuous monitoring data. So they apply all kinds of sensors and start measuring a lot of parameters. Then they may take imaging data, CT scans or X-rays. And after some procedures, diagnosis, okay, then you have a discharge summary. And outpatient data, here the events are discrete. Discrete in the sense, today they may go, then 1 week later, again a second visit, okay, 1 month later, another visit, maybe 6 months later. So these are all discrete visits. Then again, what is the data log? Symptoms, diagnoses, lab tests, medication, prescriptions. This is all for outpatient data. Then we may also have longitudinal EHR data. Okay. So now you know lots of, like, first visit, second visit, third visit. You have a form after the form stat in your file. And all of them are related to one patient, I think. So how is all this data, which I was talking about, okay, how is all this data of interest to researchers like us? So there is time-based information. Temporal information means time-related information. Say, for example, look at the research paper below. It's a very interesting paper you can go through. So it's learning from longitudinal data in EHRs and genetic data to improve cardiovascular event prediction. Means heart failure event prediction. So this is a deep neural network based. So what do they do in that paper? Quite simple. When compared, except for the data representation, other models that they are presently using are all that we have studied in our, or we teach in our classes. So the temporal information in longitudinal EHR data is divided into 1 year slice window. You can see here T1, T2, T3. So 1 year slice window. So here you have 7 such slices. So the temporal information means all the patient related information, whether it is diagnosis or lab related reports or the drugs prescribed, all of them in 1 year, the next year, the next year, and so on. So now a few years like this is the observation window, and you may predict based on the parameters that were measured in each of the years. Now there may be a prediction for the future. Okay, something this you can treat it as a training data, the observation window, and this is prediction. Okay, you're building the model with this 7 years data, and now you're predicting for future. So what is done? Well, these authors, they have used some machine learning algorithms and deep learning algorithms. And what did they do? So they generated feature vectors. So they extracted the median, maximum, minimum, and standard deviation values in each of the years. That slice window, which we called. And then if there are any missing values, so if some measurement was missing, then the closest date means either the next visits information or the previous visits information was used to fill those missing values. And then for so then their target was like they have used a binary value to indicate whether or not an individual had each diagnosis or prescription in 1 year slice window. Oh, sorry, I didn't share the tab. Sorry. Hope you could have told me. Huh? Yeah. So yeah, this is what EHR I was talking about. And yeah, so there's the window, observation window, and there's the prediction window. Okay, and aggregate values for each of the years is calculated, and then the feature vector is will. Okay, these are given as inputs to our ML models. And also for convolution neural networks or LSTMs or recurrent neural, any deep learning based model. So again, you'll build a tensor out of these temporal values and then feed it to them. Okay. So this one very interesting paper you can start with. So can you see the screen, all of you? In the middle, I forgot to change the tab. Anyone?
Yes, ma'am. We could able to see.
Yeah. Okay. So now you know about the training and the prediction. Then the data that we have, okay, it is based on different formats and standards. So all the data sets that you come across, like ICD means International Classification of Diseases. This is framed by WHO. And then CPT is the current procedural terminology. LOINC is logical observation identifiers, names and codes, like we have seen in the patient identifier. Then for drugs, you have a format, a standard for generating the codes, like National Drug Code. And then SNOMED is systematic nomenclature of medicine. And then UMLS is Unified Medical Language System. So when it comes to Indian health related standards, you have this term. Okay, so you can look at the website National Resource Center for EHR Standards. So all the information is given. So okay, so this is about the SNOMED, this is about the LOINC, this is about ICDs and all those. Then the DICOM standards for imaging, images, waveforms, audio, video. Okay. So so if say someone is performing an angiography, then they give you a video, right? So that video format, what it should be, there are standards. So every data that is generated is as per some standard. So any device manufacturer uh, who capture data for health related applications, they need to follow these standards. So these are about the standards. Now, how are these standards important? Say, for example, we come across a lot of diabetes patients. So ICD-9 code for diabetes mellitus is 250.02. So this is an identifier. You have hundreds and thousands of issues with which the people go to, and now you have an ID for each of them. Similarly, ICD-10 code for coronavirus is B34.2, and for creatinine, when you undergo some tests of kidneys, the lowing code is 2160-0. Similarly, NDC numbers are used in drug and supply chain. Okay, 500 mg thing, they have a code for it. And similarly, SNOMED code for arthritis, gouty arthritis is something like this. This code, they can track the stock they have. Okay, so in the whole, a portal, the ID is used. Then, yeah, one more thing is ICD-9 has only a few thousands of codes, I think, but ICD-10 has got several lakhs of codes. It's when I go through the literature, I often feel like IPv4 and IPv6. Why IPv6? We have a lot of IoT devices. We need an identifier for each of the devices. It's the same. Now the are increasing. Okay, there is a growth in the types of these entities. So you need an identifier. Yeah. So unified medical language system. There are some sources like Meta Thesaurus, in which you have 1 million biomedical concepts from over 100 sources. And semantic network, it's more than just it's more like more 135 broad categories and 54 relationships between the categories. And then there are lexicons. I have told you, I have shown you one website in the beginning. So lexical information and tools for language processing. So this is a specialist lexicon related to medical books. And how about deep learning applications to these electronic health records, for which you have a lot of standards, lot of clinical related stuff, lot of procedural related stuff. So what we need to do is we need to transform the longitudinal electronic health record data into input vectors. Okay, once you can design that input vector, the remaining things follow easily. So how do you transform it? As you can see, you have some one hot encoding related stuff. Okay, and for each of the keywords you have, will generate a vector. Okay, all such vectors put together, you'll be giving as input to the neural network model. Then we need to assess the sample size, number of clinical events, existence of labels, and use of longitudinal data or temporal data. Then handling of data quality, like how do you pre-process it. So what are the activities that we do with EHR data as input and to a deep learning model? So the target task could be disease detection. You can see on the right, disease detection, or it could be sequential prediction of clinical events. So what next? Today there is cough. Tomorrow it could be pneumonia or COVID. Okay, so sequential prediction of events. Then concept embedding. Okay, you have patient concept, you have clinical note concept, you have doctor related concept. How do you generate embeddings for them? Okay, next is like you can have data augmentation. Sometimes you may have very limited data, so you may have to go for data augmentation to train your models well. Then it could be data privacy. One activity could be data privacy, because most of these patients' data is sensitive data. Most of the columns are sensitive. So we have to preserve their privacy. So now your neural network model goal could be to preserve the privacy. So these are the different things we can do with EHR data. So this is detection and classification. The first one that we talked about, the first target. It refers to the task of detecting whether specific diseases can be confirmed in the EHR data. So the goal of developing a deep learning model for disease classification is first take the input EHR data and then feed it to the deep learning network and then get the output disease target. And of course, there might be many hidden layers in between. And data sets, there are a lot of data sets available. So very difficult to pronounce, but pooled resource, open access, amyotrophic lateral, okay, all that stuff. This is clinical trials data. Or you may have something like Parkinson's related stuff. Okay, and certain data, they are binary classification data, certain are multi-classification targeted. Then we also have a lot of multivariate time series related data like EEGs and all. Then we also have a lot of models already developed which are based on LSTMs for mimic. Okay, that is another intensive care related data. So certain models have also started making use of GRUs, attention models. Okay, people are trying to apply all kinds of deep learning models to this EHR data. So that is about disease detection and prediction. So what is sequential prediction? So this refers to predicting future clinical events based on past longitudinal event sequences. And you're trying to establish a relation between past data, means historical observations, and the future events. So yeah, there are a lot of published works again for cancer related, heart failure related, okay, diabetes related, COVID related, skin issues related, lot of things. Yeah. So before going to the next topic, let me show you some simple models. And just sharing the collab sheet. Give me a minute. So this is some stuff which I've taken from the web. I think the origin was Udacity related stuff. So patient selection from EHR, electronic health records are used, and then patient is to be selected for some diabetes for clinical trials. So this is related to drug related data. You can see here, I've just mounted my drive onto this collab sheet, and most of you are aware of it, right? And then I gave the path. So all my code is in GMR deep learning folder, and so I have just appended the path, and then I started importing all the necessary packages and functions. And then it's just to check whether I'm getting it. So then loaded the CSV file into this. And this is how the EHR data so okay, so this is about the encounters. So the encounter ID, the visit ID, and country, gender, age, weight, admission type. You can see lot of stuff. So some diagnosis code I've shown you, like COVID code and diabetes code. There are, right? Other diagnosis codes means there are multiple issues. Okay, and then how many times he came in as an inpatient, how many visits as an outpatient, number of medications, how many procedures were carried out on him, and some stuff. Some NDC code, this is the drug code, which was administered, what medications were given to him. So now in the EHR data set, it is hierarchical. So we have some levels, line level, encounter level, and patient level. So how many times he had visited, right? Then how many unique encounters, and yeah, this is just the data frame stock view. So then select a patient who has more than one encounter. So then we have a few patients whose age is in this range and are females. And this is all from that electronic health record. So yeah, so then we group because we need to check which drug is administered and all the stuff. Okay, then pre-processing of the data. So we are replacing any missing values with none. And then we check the distributions of these data. So we would like to know each column, if it is numeric, how is it like? Okay, so we run these. So these are all the different column names. And so we'll just plot the distributions. So age, you can look at this. So it's not purely Gaussian. So number of patients below 40 age is limited, and after 50, number of visitors beyond 50 age is more. Then we can also have some more information. So this tells you how many outpatients, how many inpatients, emergencies, lab procedures, diagnoses. Okay, this is a simple plot. Okay. So how many lab procedures were carried out, and number of medications, number of procedures, number of diagnoses. Then how many patients readmitted and administrations of certain drugs. Okay, how much time in the hospital. You can see more number of people from till 6 days, and beyond 7 days there are few people. So like this you can execute a lot of code on each of the patients. Okay, and then find out how many times is repeatedly coming, what drugs are administered, and all that stuff. So we'll talk about a few more. This is run. So these are the NDC codes, okay, drug-related codes. This is all from EHR data. Okay, dosage form, oral or through injection, tablet, and all those. And the IDs, of course. So there are 251 NDC codes and 24 proprietary names. So how many unique patients? And how many are first encountered? Yeah. So I think we'll stop with this. Now you know EHR data with simple Python code. Like any other regular code, we can process it and do our exploratory data analysis and do the stuff. So, yeah. How many drugs? The list of general drugs, their codes, and all this. How many were administered with it and all that stuff. Okay. So later we can collect the features and then build the feature vectors and then make our neural networks learn. I'm sharing the presentation. So then now we know how to process the data and start building the feature vectors. Or once you get the input processed, you can directly give to deep learning models to extract the interesting patterns. Then sequential prediction, it refers to predicting future clinical events based on the past longitudinal event sequences. So that means you would like to know if uh, 6 months back's data, 2 months back's data, today's data, you'll be able to predict that it is a likely case of heart failure. Okay, that is sequential prediction. So now, how about representations of this information? There are concept embeddings, like what you have already like teach them in the DWDM course. Right? Concept embedding is algorithmically deriving feature representation of clinical concepts or phenotypes as they are called from EHR data. So let us look at a few of them, few of these embeddings in the later slides. Next is about data augmentation we were talking about. So we can make use of GANs, generative adversarial networks, and then generate extra data, additional data. And for data privacy, we may make use of de-identification or anonymization techniques. So the next is which models to apply. We can make use of feed-forward neural networks, or and we can have fully connected neural networks and sigmoid or rectified ReLUs, okay, as activation functions. And we can make use of RNNs and for processing variable length input sequences. Or we can make use of Boltzmann machines, which are bipartite neural networks. It consists of binary stochastic modes. So what is the advantage? They can capture the latent representation of the input data. Okay. And then GANs, as I told you, we can generate synthetic samples by training the generator, and then they discriminate it. So finally, within a threshold, or as long as the discriminator is able to identify its fake image, so the generator keeps generating. Then CNNs, they capture the local features of the input data and stack those features up via a sequence of convolution to derive global features. So let me show you one. I'm just loading the sheet. So this is COVID data set. The link I have given here. I'll share the sheet with you. So trying to mount the tray, just a second. Can you hear me?
Yes, ma'am, we can hear you.
Someone overrided me, I think. Is my screen visible?
Oh, madam, screen is not visible.
Any issue?
Yes, ma'am.
Any problem?
No, madam.
You are
Now it is
controlling the
visible.
screen or what?
Yes, madam.
Just a second. I'm sharing it. మందేనా వాళ్ళది కూడానా అదే అదే can you hear me?
Yes, madam. Now we can hear you.
మధ్యలో ఇక్కడ వైఫై ఇష్యూ వచ్చినట్టుంది క్యాంపస్ కి. సో ఐ కనెక్టెడ్ ఆన్ మొబైల్ నెట్. I'll share this screen. I'm running the sheet. Yes, so let me share. It's set now. Can you see the screen? So now you can see 3 folders, right? You have COVID folder, normal, and viral pneumonia. Just remember this. Okay, so I'm using this sheet. I've taken the COVID data set and I have put it in this folder. Okay, so I've gone to the home folder GMR_DL. I have mounted it onto the drive, right? And so I have used a seed of 1337 and have split all the data into 80, 10, and 10 for training, validation, and testing. So how do you make out that? Okay, so I've taken the COVID data set, split it into 80, 10, and 10. And how is it like? So the whole COVID data set, as you can see here, when I go to the COVID folder, okay, so these are the images that I have, which are labeled as COVID, right? And I have, these are all the images for normal. And these are labeled as normal. And these are labeled as pneumonia. Okay. So this is the data set. So I'll tell you about how to process these images and train a model. So these are the 3 folders. Now coming back to our code. So what do we do here? We split that data in all the 3 folders into 80, 10, and 10. Total there are 150 files. Then, so we rescale the images so that all of them, they're normalized. And we are now reading images from the train folder. Okay, whatever 80, 10, 10, how is it divided? So I'm going to the split, and that function now considers in the test folder, we have COVID, normal, and pneumonia. So I have how many? 5 images here in the test folder. And for normal, I have 5 images in the test folder. And for pneumonia, 1, 2, 3, 4, 5 in the test folder. Right? So in the test folder, I have 15 images. And in the train folder, again, training, you require more number of images, right? And in the COVID class, I have so many. In the normal class, I have so many. And in the pneumonia class, I have so many. Right? So this is about train, okay, test, train, and validation. So validation also, it's okay if I have limited number of images. Now you are understanding. So I have a whole set of COVID data set, and I have all the images in COVID, normal, and viral pneumonia labeled as these 3 classes. Now I'm splitting them into 80, 10, 10, so that in test and validation, I have 10% and 10% of the images, and in train, I have 80% of the images. So let us go to the code. So this is what it says. Total, there are 150 folders, and I am dividing into 80, 10. What next? So now we are putting them in split train, split validation, and split test, the images that I have shown you. So we have 120 images belonging to all the 3 classes for training. You must have noticed in train folder for all the 3 classes, we have lot of images, and 15 in train test and 15 in validation. Okay, so total are this. Now we are starting to build a model. So what is this model about? So the input shape is 128 by 128, 3, and we have dense layers, right? So you can see we have 2 dense layers out here, and we have a for each of them we have a ReLU activation, and then for this is a multi-class classification because we have more than 2 classes as target. So we are using a softmax activation. It's a routine deep learning model. You now know anyway how to calculate the parameters and all. So then we use simple, Adam, which is one of the best optimizers we have. So why do we use Adam optimizer? Yeah. So it is to optimize the weights, the best combination of weights, right? And we are using categorical cross entropy to compute the loss. And using a simple fit function, right, with 100 epochs and giving this train data. And look, I just trained this, and I'm saving this model so that I can have the weights stored. So later, sometime later also, you can use these weights or use these weights for transfer learning. Yeah. So I'm loading the weights and then simply plotting the training and validation accuracies. Okay, so training is the blue one and the validation is the red one. These are the losses. And yeah, we are also using the test folder images, and then we got this accuracies. Okay, so 92.24 accuracy. Now you can literally try with other optimizers and adding a few more layers and dropping out. Do all the things that you wish to do on this model to bring about a better accuracy. So this is the simplest kind of a deep learning application for COVID images. Right? Hope you got this. Right. So we come back to our embeddings. So this is simple neural network, and you can also make use of embeddings so that you can represent this data in a particular form and then feed them to any of the deep learning models. So what are these embeddings? Hope you can see the screen. Yeah, what are these embeddings? So word2vec, most of you are familiar with. What is word2vec? What is word2vec? Anyone? Can you listen me?
Yes, madam. It is converting textual data into vectorized format, madam.
Yes, yes. So it converts documents to vectors of words, right?
Yes, madam.
So in medical applications also, right, you can have a word2vec representation. So you are trying to represent these words out here. Like, for example, you have bronchitis, pneumonia, obesity, lot of stuff. So in general, one-hot encoding, what do? You have, say, you know this representation, right? So you'll have, if you have n words, you can have n-dimensional vector. So this is one-hot encoding. Now, when it comes to some patient data, so there can be an input of a set of one-hot vectors. Like, for example, for COVID-19 to happen, the other words initially in the record will be like cough initially. Next event could be fever. Next could be shortness of breath. Next could be chest pain. Okay, now all these, a sequence of one-hot vectors can be generated, and that is a patient record. Okay, so now when somebody comes for a chest X-ray, with that X-ray image, you must be able to now predict it is pneumonia and later on maybe COVID-19. Okay, So the issue with this is like all of these are at the same distance. So when you consider them, bronchitis, pneumonia, and what is bronchitis, pneumonia, and obesity. So pneumonia is one. So the distance between these two and these two is the same. So there is no distinction about similar and dissimilar words. So distance between obesity to pneumonia is the same as distance from the pneumonia to bronchitis. So because of this, in one-hot vectors, we make use of word-to-vec. And that is where you must have heard about continuous bag of words, skip grams. So we apply these skip grams, okay, to these patient records. And how are these? Like now, coming back to the same data. So if you have this cough, fever, chest X-ray, these are the like if you start with fever, right? Now the events, you can take a window. You can take a window, so one on either side. So then the neighborhood concepts would be cough, then benzonatate, pneumonia, chest X-ray. Okay, this window will be considered as a neighbors. But when you take slightly slighted window, then what do you have here for pneumonia? So you have 4 items over here, and it doesn't start with cough, it starts with benzonatate and goes on to amoxicillin, right? So given pneumonia, these are the neighboring concepts. Given fever, these are the neighboring concepts if you're taking 2 as the window. So this is how we can represent the diagnosis and medications procedures in multidimensional real valued vectors. So there will be a kind of a latent relation between them, unlike the one-hot vectors. So there is a kind of a similarity between these events. So there's the model architecture for skip-gram, as you can see. So a d-dimensional one, right? So how is a patient record represented? So it's like, all the medical concepts, they're summed up. Like, for example, here, take the first one. It represents the medical record of a patient on a timeline, like the earlier example we have taken, right? And you take the second diagram, it is the medical concept vectors. Okay, benzonate vector, cough, fever. So these are the different concepts vectors. And what is a patient record now? So patient record is like cough is the first vector, right? So take this concept vector. Okay, in the patient record that gets added in the beginning. Next is the benzonatate. So that gets added up next. So a combination of all of these vectors is the patient's representation. Okay. So now when such a program, such a set of vectors is given as input for learning the medical concepts, right? then you get some, so TSNE is applied, okay, and you can see the distinction there. So if it were one hot encoding or direct representations, then both these skin diseases, the blue and the red one, they might be like falling at a particular place. But here you're trying to represent it in a vector in a slightly different version. Now these two classes, they're far apart. That is the advantage of this kind of a representation. One popular embedding for medical field is the Med2Vec. This Med2Vec can be directly applied to EHRs. So because in electronic health records, the visit sequences of patients include multiple concepts. So every visit will have some diagnosis, a procedure, a medication code. So it's not a simple set of words, but it is a set of multiple concepts for each visit. So now this structure provides two types of relational information. What is that? When this patient has visited, sequential order of visits, and within each visit, what are all the codes that are occurring? Be it medications, be it procedures, be it diseases, diagnosis. So a bunch of all of them in some kind of a relation, all of them are for one visit. And every visit is sequential. Okay. So what is the advantage of Med2Vec? It not only learns distributed representations for both medical codes and visits from a large EHR data set. And so the advantage is like it has more information represented in the embedding. So it's directly like a skipgram model architecture. So for every word WT, okay, V of WT is the vector representation. So what do we do here? We find the vector representation of words, which are good at predicting the neighboring words. So this is the actual architecture of the Med2Vec. So visit after visit, these are all sequential. Each visit, there are certain diseases, certain drugs administered, certain procedures carried out. All of them, they co-occur with each other. So there is more information embedded in this. So how is it technically done? So this has been published in a paper, Med2Vec. Embedding methods. Just a second. Yeah, this is the paper. Multi-layer representation learning for medical concepts. So what do they do here? So the structure provides two types of relational information, sequential order of visits and co-occurrence of the codes within each visit. Okay. And how is it done? So you can see here. This is the structure of Met2Vec. Okay, so here this is a visit. Okay, and this visit is converted to some codes xt belonging to 0, 1, right? Every visit is encoded as a sequence of codes. So then, yeah. So you have some binary coding, then an activation, right? That is combined with some place, demographic information from Vizag, from Hyderabad. And all that, again, a ReLU over here, and then a softmax. Okay, so this is the Met2Vec structure. So this is the intermediate level representation. This is the visit level representation. And this D is the demographic information. And ReLU is used so that you don't have the minus values. So with this Met2Vec, again, you have better classification results, right? Then the next kind of embeddings, they are multi-level medical embedding of EHR for predictive healthcare. So what is this multi-level medical embedding? Just a second. So this is mine, and so this learns the multi-level embedding of EHR data while jointly performing auxiliary prediction tasks. Okay, so it's like this. So it's not just directly combining all the data into a visit, but there are two more. I mean, there is a hierarchy in each visit. Okay, so in a particular visit, there can be multiple events associated, and each visit is a temporal visit. Okay, so temporal is captured, and also hierarchical structure is also captured. And in the hierarchy, you have two levels, diagnosis level and the treatment level. So you have more knowledge embedded into the representation. So now you can see. So there is an interaction between. So you can see a lot. This is treatment level, the lowest one. And all of these, they are combined to input to the diagnosis level, and several such will be added up to a visit level, and then most of such visits will add up to a patient level. Okay, so you have different treatments, different diagnoses, right? The next level, pinkish level, given as input. Then after that, every visit, okay, and then after that, for every patient. So you have more knowledge represented out here. Then one another interesting representation is Dr. 2Vec. So this is again a very interesting paper, as you can see. What does it do? How do you construct the right doctor representations? And how to use that doctor's representation to solve important problems. So it's like the advantage with this doctor to work is like you can identify the right doctor to conduct the trials. Okay, based on the patient and the trial description. So yeah, this is very interesting too. This is another kind of a representation for doctor related information. Okay, so this is about processing the doctor records and the trial data. Okay, who will administer and all that stuff. Then those of you interested can go through this. Yeah, it makes use of dynamic memory networks. This one interesting strategy. So they make use of attention mechanisms. And then we have another representation called patient to wake. So this is another recent paper. So it's about representing the EHR data, longitudinal EHR data, which is for each patient. So how do you represent a patient? Okay. So again, so these are some of the representation methods, embeddings rather. And yeah, I think we're almost, yeah, any doubts on this? So we'll stop here. And so we could learn what EHR data is, and we could perform exploratory data analysis on the EHR data. Okay, and then we talked about how EHR data can be processed and features can be extracted using several deep learning models. We also spoke about a small program on how to process X-ray images, simple image processing stuff using neural networks. And then we talked about different representations like med to wake, word to wake, and what else? Patient to wake, doctor to wake, mind. Different embeddings for different entities in the EHR data. Hope that was useful. So I'm sure this will be your first step. So this is at the basic level. And now you can start over from here, either directly to models or start with EHR data and do some stuff and then apply a model. But processing images and all has become routine these days. So I think it's advantage and useful if you go through EHR data. For scholars and researchers at the first step of their thesis work. That's all from my side. If you have anything to ask, I'll be happy to.
Thank you very much. Thank you very much for the session, madam. Now, to all dear participants, I want to request if you have any query, please ask.
Or you can also post me later if you think 5 o'clock. It's almost 2 hours. So yeah, I'll be happy to answer offline too. You can send me a mail. My mail ID is vallikumari@andhrauniversity.edu.in.
Okay, so I hope Okay, the summary of the session we can tell today we learned about simple deep learning models, regulators data, and we have also learned about EHR and deep learning to EHR, including how to transform longitudinal EHR data into input vectors. In deep learning to EHR, we have learned about disease detection or classification, what is sequential prediction, what to wake from for medical applications, med to wake EHR embedding, why do we use med to wake, and we have also learned how to transform longitudinal EHR data into input vector. Therefore, we learned about MIME, that is multi-level medical embedding, and what is doctor to wake and patient to wake. Thank you, madam, for this insightful session. So I think we can close the
There will
session.
be overlap with other speakers, hopefully.
Yes, madam. Okay, so I think we can close the session now. So if still you have any queries, you can post to madam, as madam already informed. So okay, thank you everyone. Thank you, madam, again for this informative session. Thank you.
Thank you. Can I leave?
Yes, ma'am. Thank you.
Can